So today, inshallah, we will start with lecture 3, combinational circuits. We will cover NAND, NOR, universal gates, and also XOR and XNOR gates. And we will check the odd even parity at the end of the lecture. Also, we will cover the electrical characteristics, multiple levels circuits, combinational circuits, analysis and design, and we'll see some new concept in design, which is design hierarchy. We'll talk about some of the CAD tools, and last thing we'll see how to make design procedure. These are the contents of today's lecture. First, we'll talk about the universal gates. The universal gates, they are the most commonly used gates in combinational circuits, which are NAND and NOR gates. Actually, they are good because they have electrical characteristics better than other logic gates like OR and AND gates. For example, here NAND gate can be used for common discrete logic. For example, here this is just NAND gate, which is AND converted, the same as AND but converted. This is in the AND it is 0001, but in NOR in NAND it is 1110. Any digital circuit can be designed and realized using only AND or NOT gates. Any circuits. If we can prove that NAND gate can emulate AND or NOT, then we can prove that NAND gate is universal. So any gate can be, any logic can be controlled, or any control logic can be designed using AND or NOT. So if we are able to say or to represent AND or NOT using NAND, so it's good. We can say that NAND gate is universal one. For example, here, the NOT is easy one here because just to convert the input X to X dash, we don't have single input NAND gate. This problem will be solved in the next slide. Here we can also represent AND gate by adding converter at the end of the NAND gate. So NAND gate together with a converter is giving negative of negative, which is positive, or complement of a complement, which is the original variable. The OR gate can be obtained using the NAND gate by adding converter to each input variable. So we have two input variables here. We can convert the first variable, we convert the second variable, and then we can have the OR gate. What about this problem? We can solve this problem by actually, if you see this table, you can see from NAND gate that we have the inputs which are X and Y, 0, 0. If they are equal, the output will be the conversion of it, and also if they are equal and they are 1, then the output will be the conversion of it. This means we can attach, as you see here, we can tie the two inputs. So we have here 0 will output 1, 1 will output 0. This is a conversion. So we attach the input together and tie them together to be one variable, and this is exactly the same as the inverter. Now we obtained both not and or. So we have the conversion here, or the inverter here, is simulated by NAND gate using the method of attaching the two inputs together. So we have here this truth table is equivalent to the inverter truth table. The also NAND gate can we can have the AND logic using a NAND gate together with an inverter, and we saw that the inverter can be obtained by attaching the two input together, so we have an inverter. Also, the OR logic can be obtained by inverting both inputs using an inversion, and that inverter is used or obtained, sorry, obtained by attaching the two inputs of this AND gate, of this NAND gate. We attach the two inputs together, we have an inverter, we invert the input X, we invert the input Y, then we have X dash, Y dash, our input to another NAND gate, then we have the output to be X or Y, which is exactly the OR gate. So that's why that's why I'm talking about analysis and design. And if you don't understand analysis and design, is like we take the input from the user, we take the ability of the user, the client, so is not user, is client. For example, if the client is a traffic police and they ask you to make a traffic logic for traffic lights, they ask you to do that. So the client has requirements and they have budget, they have limitations, they have constraints. One of those constraints may be telling you that they only have NAND gates. What will you do? You want to implement the entire circuit using the NAND gate. This way, if you understand today's lecture, if you understand this slide, you will be able to simulate the entire logic using only NAND gate. That's why we say about design. Design means that you take whatever the client have, they have budget, they have material, they have whatever they have, or they have specific requirements and they have limitations. You talk all these constraints and you come up with your design. It is not like you design whatever you want. No, you design whatever the client wants, not your imagination. That's why I'm enforcing you to understand what the meaning of design. Also, the NOR gate can have the same effect. It can have a universal effect. If you have only NOR gate, you can convert on using the same concept, which is attaching the two input together. This means if you attaching the two input together, you will get an inversion. Also, if you have attaching these two input together, you will have the inversion of it, the complement of it. You can have the OR logic using the NOR gate together with an inverter at the end. You can also have the AND logic using inversion or inverter at each input, and then having the input after conversion is attaching to the input of the NOR gate, then you will have the AND logic. So you can have the same I mean, you can implement your entire logic with only NOR gate. You can also implement the entire logic using only NAND gate. How to convert any circuit. For example, how to do that? You better do the following. You better implement your circuit as AND or NOT gates first. Then start to apply this conversion. So it is better to make your truth table, then Karnoff map, then the expression that you have, then implement your gate sketch. You make a gate sketch, and then using that gate sketch, you can convert to all NAND gate or all NOR gate. We will take here an example to convert to all NAND gate. The idea is simple. If you have NAND gate, you can have NAND and NOR gate. They have special characteristics, like easier to fabricate using CMOS technology. This is one of the characteristics that is very important in NAND and NOR gates compared to the corresponding and OR gates. Uh, there are some kind of rules applied to convert Boolean functions using and or and not into an equivalent NAND and NOR logic diagrams. We'll see some kind of this conversion. As I told you, you just remember that I told you, you just sketch your logic gates using and or and not. Then start to convert to all NAND gate. You can do that. Or this is the only way to do it. For example, if I add two knots here at the beginning, so we have this is uh, x, uh, this is exactly as converting both inputs, and the NAND gate will be obtained by having these two inputs and together with an invert. Okay, sorry. This is the conversion of these two inputs. We still need some kind of inversion at the end. This is x dash or y dash. If they are complemented, we will have, yes, we will have the AND logic. Okay, let me tell you the way to convert. This is the way to convert. Just add, you have, okay, you have here this circuit, okay? And you want to convert this circuit to all NAND gate, okay? We agree on this. You can have this circuit out of Karnoff map or whatever you have it. You have the Boolean expression, then you draw your sketch. This is the sketch, the first sketch of your logic gate. What will you do? Just add bubbles here, two bubbles here, another two bubbles are added here, and then you have this, uh, you have this sketch. This is the second sketch. You didn't do anything, just convert the output here and convert it back. There is no change. Converted here, then converted back, there is no change. And you just remember that I want you to concentrate on this slide because here, this one, not this one, actually, this one, okay? If you want an AND logic, if you want an AND logic, you have to add conversion to the end of the NAND gate. If you want an OR logic, you convert the two inputs. You convert the two inputs. So continue this procedure. We add bubbles, okay? like that. We add bubbles like that. Then we have here the first one is NAND gate. It's okay, it's NAND gate. It's converted to NAND gate. This is NAND gate and this is NAND gate. The remaining is this one. This is the input to the OR gate is converted. The two inputs to the NOR gate is uh, is converted. This means this is just an AND gate. Because I told you, if you want the NAND gate, you just convert the two inputs to the NOR gate, to the OR gate. Converted the two inputs to the OR gate means having NAND gate. Okay? Again, this is very important. Again. I want to convert this circuit to NAND gate. The client has only NAND gate and he asked me to use these ICs. The ICs, he has many ICs and these ICs are NAND gate. He don't have OR gate or AND gate. He only have the AND gate. So I sketch my logic gate using the and no and or and not. Then start to add bubbles between each gate and the next one. For example, here we add two bubbles here, and here we add two bubbles. These bubbles represent an inverter, and inverting of an inverted variable is having the same variable again, or negative of negative is positive, the same as that. This is just doing nothing, just to convert the signal and convert it back doing nothing. Doesn't have any effect on the logic. Then we have here, okay, that's good. We have NAND gate here, we have NAND gate here. What about this one? This one is exactly NAND gate, because if you have, we can draw it here to make you understand. Just make it simple. We have NAND gate, we have X and Y, and this is 0, 0, 1, 0, 1, 0, and 1, 1. This is 1, this is 1, this is 1, this is 0. This is NAND gate. What about if I convert the two inputs and OR them? So let me convert the two inputs. So this is X dash. So it is 1, 1, 0, 0. And I convert Y. So I have Y dash, which is conversion of this is 1, 0, 1, 0. Okay, about OR them together. Or means because we have the inversion of the first variable, the inversion of the second variable, ORed. So we OR the complement of the first variable, we OR the complement together with the complement of the second variable. So we have OR function. Here is 1, this is 1, this is 1, and this is 0. It's exactly as NAND gate. This is the NAND output, and this is the OR output. They are the exact thing. So this is exactly this is exact NAND gate. That's why it is NAND gate. I'm saying that because it is already now you can have NAND gate. This is exactly equivalent to that one. Okay. Now about this one. Can anybody help me to do it? The first step is to do what? The first step is to do what? Are you there? Anybody there can answer me? You hear me? Hello?
Yes, doctor. Yes.
Yes. So the first thing, what should I do right now?
Dr. CD inverse result
You add what?
CD get and get.
And again, no, I told you about adding something else. Muhammad Jum'ah,
Yes.
I said the first step is to do something. Add what? Adding something. Okay. I think we have an answer here in the chat. I don't have mic because I'm using. Okay. There is no problem. No problem is okay. You can share using chat. No problem. For the question again. Now I want to convert to this circuit into all and NAND gate. What should I do? Can you answer me? Okay, again, I will reverse back to this slide and please concentrate to answer the second part. I have this circuit and I want to convert this circuit to all NAND gate, as you see at the upper, the name here, the top, the title. This is the beginning. We begin with this circuit because we have our logic. I get the logic from the client, and the client asks me to do some specific control. I do the truth table and Karnaugh map, then I get the expression, the Boolean expression, then I draw my sketch. This is the sketch of my circuit. I want to convert this from and OR gates to NAND gate only. The first step, again,
Add
I will tell you the first step.
inverters, doctor.
What?
We can add inverters.
Yeah, you can add inverters, as Muhammad
Yeah.
Abdul Majid said. We add inverters at here's the beginning. We say is bubbles. We can say bubbles.
Yeah, Papa.
You can add two bubbles here, and this is two bubbles, another two bubbles, and then you have conversion of inverting an inverted variable, which is the same as saying negative of negative, which is positive, returning back to the same. This is equivalent to that one.
Yes.
Okay. And then we have NAND gate here and another NAND gate here. And if we concentrate on this OR gate with an inverted input, it is exactly an a NAND gate.
None.
Now I
Yes.
have, yes, exactly. I have converted all things here to NAND gate. Okay, move to this circuit. Can you tell me the first step to do what? Anybody? Anybody can tell me add what?
Doctor, invert the CD, the first not the first gate,
Yes.
and invert the input for the OR,
Yes,
the
yes,
first
exactly.
OR.
Thank you, Muhammad.
Then,
Thank you.
welcome, doctor.
Thank you. The first thing is to just add bubbles. And these bubbles, we don't add bubbles at the beginning. We don't add bubbles at C and D. We don't add bubbles at B and A, and we don't add this. We just add bubbles here. You see these places, those places. We add bubbles here because if we add bubbles here, we don't have an effect on the logic. The logic is the same. Now it is easy to convert everyone here to an AND gate. You have an AND gate already. This is an AND gate, and this is also an AND gate. There is no way, there is no need to convert it to an AND gate because it is already, you know that it is an AND gate. Just add bubbles. But you have a problem here because you added bubbles. This one, this bubble is a problem here. This one is a problem. because it is only one bubble. They are not two bubbles. The number of bubbles should be okay. The number of bubbles should be an odd one because this is not covered by another gate. It is it is a problem here. This is a problem. If you forget about it, you will have a problem because this one is okay, that one is okay, and that one is okay. But that one is not okay because you have to find a way to add another NAND gate. So the solution of this problem about B dash is just to do what? It's just to add an inversion, which is the same as adding NAND gate like that, NAND gate with the two, the two input of it attached to each other. So it is adding NAND gate with the two inputs attached to each other. This is should be done. This should be done to avoid having only one bubble. Only one bubble is not good because you changed the logic of the initial sketch of the gates. You changed it. If you change it, this means that you changed the logic and your circuit is not going to work. So a solution of this problem is just to add another NAND gate and attach the two inputs of this NAND gate together and have an input to that NAND gate.
Doctor,
Yes,
if we delete the last two bubbles in the OR and we put one bubble for the output, it will be the same.
if we delete that one, this is
Yeah, and
NOR gate. If you have NOR gate, is okay, but you have also the problem of having one bubble here because you have to make this if you okay, let me concentrate on what you are saying. You are saying remove those two bubbles, right,
yes, and
and
add
add
one
one
bubble
bubble
there.
here.
Yeah.
This is not correct because you are not you are changing the logic. You are changing the logic of the gate, or you
Ah,
are changing the control of the gate. It will produce
okay.
another control. But also, maybe you don't have NOR gate. You have only an NAND gate. If you have NOR gate, there is no need to do it like that. You can better to add or to convert the two inputs to have NAND gate.
Ah, okay.
This is good solution if you have NOR gate. But also you have to concentrate because you have changed the logic. So you have to see how to make equivalency to make the equivalency to the original logic. You
Okay,
understand?
doctor.
Okay,
Yes, yes. Thank you.
welcome. So this place has a problem, as I told you, and you have to solve it using a converter. Okay, okay. He just said that B should be B dash. This means it is converted. Should be converted. That's it. He didn't say we have NAND gate and we attach the two inputs of the NAND gate together to have an inverter, but he just simplified it and saying this is complemented. B dash is complemented. Okay. What about some electrical characteristics of the logic gates? We have the fan in. Fan in is the maximum number of inputs to a gate. Some of the gates doesn't bear more than three inputs. Maybe some other don't bear more than five, and so on. This is fan-in, and you will find it on the characteristics of the IC that you are buying. You'll see that how these are the electrical characteristics written on the sheet of the gate that you are buying. So fan-in is like the maximum number of inputs to a gate. More than this, you will find different logic than you expect. Maybe you expect zeros and ones, you will find ones and zeros, the opposite. So you have to stick to the requirement of the fan in for the gates that you are buying. What about the fan out? Fan in is the input, fan out is the output. It's how many standard loads it can drive. How many gates they can drive. This should be one. So fan out, usually one gate. So we have fan in here is two, fan out is one, fan in is two, fan out is one, and so on. Noise margin, how much noise the circuit can tolerate, how much noise the circuit can have, and at the same time produce the same or expected logic. This is noise margin. Power dissipation, how much power the chip needs for the TTL transistor logic. This is very high, but after we have the CMOS logic, we have more or better power dissipation capabilities. Binary signaling and noise margin, we have here the output can be different from logic to logic or logic gates to logic gates. But actually or typically 0 presents false or 0, and 5 volts presents true or 1. And the range here can accommodate more noise if you have higher separation of the high and low high and low logic. So you all this area can have more noise, can handle more noise. Anything in the white area will be considered as low. So the tolerance of the noise here in this one is better than the one to the right hand side, because we will not say the logic is high. Only we will say only the logic is high is if it passes 4 volts. If it is lower than 4 volts, it will be considered as 0. Okay, and the propagation delay. I told you about the propagation delay previously. We had two circuits, and one of the circuits are two levels, and the second are three levels. We said that the three levels is not better than the two levels because two levels is faster because of the propagation delay. So the propagation delay is described by the timing diagram here in the figure. You have the gate, the inverter gate, and sorry, the inverter gate has an input in and the output out or out. And the in, when the signal is coming to the in, it doesn't appear immediately on the out terminal. So here is a representation of in. In is represented here, and the out is represented here. And this is the voltage that applied on the in, and this the out voltage that appears at the out. You look at this part is important when the in is moved from low to high. When in is moved from low to high, out it doesn't directly convert, should be converted here. You can say the middle of this edge. So start conversion for should be from here, but it waits for a time. This is the delay time or the propagation time. Then we start to see the out on the out terminal. Here also, when the in coming from or going down from high to low, the out will not move from low to high immediately, but it will wait for another time. And the delay or the propagation delay of this gate is just the maximum of those two times. The maximum of those two times. I just calculate the this one, this time of conversion from high to low, and this time of conversion from low to high, and then take the maximum of them to be the time of the propagation delay. Okay, I told you we are designing a circuit. If we want to design a circuit, so we have design goals, and one of these design goals is the performance. And if you don't have good performance circuits, you are not good engineer. You are not good designer. Returning back to what is analysis and design. Returning back to understand what is design and analysis, we have a combinational circuit, and the combinational circuit has a block diagram like that. We have N input or M input and N output, and this is the logic circuit. The output depends only on the input, not other thing, because we have combinational circuits. We have another one is sequential circuits. We studied both of them in this course. There is no cycle. There is no feedback. There is no feedback from the output to the input again. There is no feedback. But for the sequential circuit, you will find the combinational circuit here has an M input and N output, and the combinational circuit output has a storage element, and this storage element return a feedback to the input again. So the input doesn't, or the output doesn't depend only on the input, but depend only also on the previous state. This is a previous state, like a counter. A counter has a count 2, and the next output will be 3, depends on the knowing that the previous one was 2 and the next one is 3, and so on. This is sequential circuit. Actually, we'll study sequential circuit maybe after 2 weeks from now. We will understand what is sequential circuit, what are sequential circuits. We will explain it in detail. We will pass by designing circuits depending on flip-flops and latches. I think you studied some of these concepts in the digital logic design, but now we will study how to make design or to design a fully working control system. This is the sequential circuit. What is the difference between analysis and design? As I told you, we start by specification and we end up with a logic diagram. Analysis just to determine or understand the functionality that the client needs, and try to implement a sketch for the circuit that is needed by the, the, the client. For example, one of the standard analysis steps here is to make sure that the circuit is not sequential, it is combinational, and make sure you are working either with combinational circuit or sequential circuit. Accordingly, you will change your design. One of the design steps is to derive the functionality of a specific circuit. If you have already implemented circuit and you want to have the functionality or the Boolean expression of this circuit, is easy to have to name the edges here by variables like T3 to T4. This edge is T4, this edge is T3, this edge is T5, this edge is T1, this one is T2, and so on. and then start to write down the functionality or the Boolean expression for each one. And coming from back to front, start name the variables until you name everything. For example, you have here A, so it's okay, B, C, and D, and T1, T2, T3, T4, T5, and that's it. You don't need any other variable. You can describe the entire circuit using the Boolean expressions, just using those variables. For example, T1 is what? T1 is B dash and C. B dash and C. What about T3? T3 is a variable of T1, which is B dash and C, and or sorry, A or T1, and say A or T1, then compensate or substitute T1 to be B dash C. So T3 is A or B dash C. And you continue driving the entire graph uh, to have expression for F1 and F2. So we have F1 here, which is A or B dash C or A dash B D dash or AD or B dash D. And F2 is equal to A dash B or D. Now also you can continue your analysis by deriving your truth table. You can, if you want, you can have the truth table without any problem. Uh, maybe this circuit is not simplified. Let me see this circuit. Maybe this circuit is not simplified, and you make sure that it is simplified. So you make the truth table for this purpose. You just reverse engineering. This is reverse engineering, just making sure this circuit is okay and the performance is okay, and it is simplified. This way you have the way back. I mean, you have the circuit, you have the sketch, and you are implementing the truth table out of this sketch. This is reverse engineering. What about the design? Design is completely different from analysis. Analysis is just drawing the circuits, making sure that it is sequential or combinational, make sure that you can handle the logic that is needed by the client. It's, if you if you concentrate with me, you'll say, okay, doctor, you are saying make sure, make sure, make sure, make sure. This is analysis. Make sure of something. Make sure of something. Make sure of something. This is analysis. After you make sure of everything is okay, you start your design. For example, make sure that you can do the logic using the given circuit or the given ICs by the client. Make sure that the performance will be high. Make sure that you have you can have the sketch of this logic gate. Some of logic gates is not easy to have its sketch, is not feasible to be implemented. Okay, if you are sure that you can have all of these, you can start the design phase, which is, I will tell you about some of the design techniques in this lecture. So the design is procedure is write a specification for the circuit and drive a truth table, Boolean equations, given the relationship, make sure that optimize the Karnoff map to have your Boolean expression. It's like starting from the first step to the last step, like you can say we are confused now because you see specification, formulation, optimization, draw logic diagram is the same as design. Yes, some of the steps in analysis is repeated in design. But the objective of analysis is different from the objective of design. The objective of analysis to make sure that everything is okay and you can handle it. And the objective of design is just to come up with the logic, to come up with the circuit. You come up with the circuit according to the constraints that you have from the analysis part. After optimization, you have your Karnoff map, you have your Boolean expression, start to draw a logic diagram or logic sketch of your circuit. This means you provide a netlist for the resulting circuit using and, or, and operators. And the technology mapping, this is the last step of design. You can have the logic gate using just a simple circuit with the ICs of NAND gates or NOR gates. And also you can use up to the technology right now is using the PCB printed circuit board, and you can use field programmable gate array or FPGA. And actually you are doing that in the lab. There you have a circuit, you have logic, and then you convert or map this logic to a specific type of FPGA. And this is the last step of design. And sorry, okay, this is the last step. Actually, we have a test. You know about the procedure. You implement and then test whatever you have implemented, and you should verify. Testing is named as verification. So you verify the correctness of the final design. You make sure that your design is good. Your propagation delay is not affecting the performance of your circuit. You make sure of everything is working and test everything. Then you have the the circuit that you are designing. Okay, now we go to specific, you can say, uh, specific procedure for design, which is design hierarchy. Some of the circuits can be designed by the logic, the Karnoff map and truth table, but some of them cannot be designed using truth table and Karnoff map. For example, if we have a large circuit or a large chip and we need to design very large logic, we use the divide and conquer procedure. Divide and conquer is simple. You have big system, and then you divide the big system into small subsystems. Okay. For example, we will take the equivalent circuit. This is equal circuit. It takes 4-bit equal. It is 4-bit equal circuits. It takes two vectors, A from 3 to 0 and B from 3 to 0, means this is 4 inputs, and this is also 4 inputs. The most significant bit is at level 3. So this is 4, 0, 1, 2, 3. This is 4 input, and this is another 4 input. And we want to compare the 4 inputs together with another 4 inputs. If we want to make it with a truth table, what we will do? We will have 256 entries in the truth table. Is that feasible? No, it is not feasible. The best way to do that, the comparator or the equal circuit, we have again we have two variables. One is A and one is B, and this variable is four bits, and this one is 4 bits. If we want to make sure or to have the truth or to make the truth table, we need 4 bits and 4 bits, which is 8 bits. We need 2 to the power 8, which is 256. We need 256 entries in the truth table. How come you will draw just a giant truth table? The solution for this is a divide and conquer, or just, I will tell you that the best way is just to make to make the design using divide and conquer is not okay. This is the classical one. Maybe using Karnoff map, using truth table is not working. So what you will do, just make another scheme of design, which is design hierarchy. This is for if I want to compare two variables with four inputs. What about if I have two variables with five inputs? I will have 10 inputs or 10 bits. This means 2 to the power 10, which is 1024 entries in the truth table. This is not going to work. This is not feasible. You cannot do that. The best way is to make formulation of each comparison. For example, I have 4 bits here. I compare the first bit here with the first bit here, the second bit here with the second bit here. So I design just one comparator and repeat that comparator on each bit. So you divide the circuit to four 1-bit comparison. We divide the circuit to four 1-bit comparison. And another circuit at the end, we have comparisons, 4-bit comparisons, and then another circuit to take the output of the 4-bit comparison to make a final decision about the variables. It's like that. This is 2-bit comparison comparator, and this is 2-bit comparator, and this is also 2-bit, and so on. This is the same logic. And another one here to compare the output from the previous comparators. What we will, what we will design now, we just design the comparator circuit, just that. Make truth table for the comparator circuit, and then repeat the same design for the 4 comparators. Okay, that's better than using the truth table, because the truth table is going to be giant, and actually you will not have the performance in the same performance as this circuit. This circuit is high performance circuit. So we have to design the MX and ME. We define the output of the circuit to be 0 if both inputs are similar, and 1 if they are not, if they are different. This is the first circuit. Is like X, it means that they are different. Okay, return it back. 1 if they are different, this is X like different, and this E is equal. We need an equal circuit. We check if they are different here. We get 1, 1, 1, 1. Then we complement the input to that 1 to get the output E, which is representing the equivalency between variable A and variable B. So we make the circuit, we are designing this circuit, this one, the mix. And this is the truth table of the MX, 0, 0 equals 0. We need, if they are similar, we say they are 0. If they are similar, we say they are 0. And if you are clever, you will get the functionality of AI, which is AI dash B plus or AI B dash. And if you are clever also, you still clever you to say this circuit is what? This circuit is XOR circuit. This XOR circuit. This one. This is XOR, the same as XOR. But why he or the author represent it using this? Because maybe we don't have an XOR, we have only OR and or and inverter gates. We don't have XOR this way. We can convert to all NAND, all NOR as we like. This is an XOR circuit. This is a simplification or representation of an XOR circuit. Now we have the first drawing of the first circuit. We can repeat that 4 times. This is easy. It's like if you have a function and you call this function 4 times, that's easy. Then we have another circuit that will take the output from the 4 circuits to make a decision about the variable. If it is equal, it will be 1. If it is not equal, it will be 0. How did we should design this circuit? Now we should design this circuit. Now we finish the 4 MXs and then we design the ME. The ME is simple. If they are equal, it will, this is MX, sorry. E is only 1 if all intermediate values are 0. It's like E, the complement of all the intermediate variables. So the design is just uh, a simple NOR gate, just a simple NOR gate. Okay. Now we have the MX represented by that circuit and ME is represented by that circuit. We reach the design that we need. Okay. You understand this example? Hey guys, you understand? If you have any question about this circuit?
No, doctor, it's
No, no,
okay.
doctor.
Okay. So you understand the design hierarchy, you understand how to make design using simple blocks, and then you repeat these blocks many times to have the logic you want. Okay, this is another implementation. You can check it, no problem. Design error check circuit. This is the last check circuit. This is the last circuit here. I think we will not need do you need a break you need a break or we can continue?
Doctor, we can take a break for to pray, and we can come back.
Okay, okay, that's good. So a break for 10 minutes or 15 minutes is okay. 15 minutes and
Okay.
then we return back, inshallah.
Okay.
Okay, inshallah.